Let's talk about the properties of the equilibrium constant. So let's say if we have a reaction where A is at equilibrium with B. Now, recall that the equilibrium constant is important because it kind of tells us the product to reactant concentration, right? The ratio between the concentration of the product and the concentration of the reactants at equilibrium. And more importantly, it kind of tells us how far a reaction goes before actually reaching equilibrium. So, for example, let's say that at 300 degrees Kelvin, the equilibrium constant for my reaction is 9.8 times 10 to the 11th power. Notice how this is a very big number. Now, the way you write out the equilibrium constant, and I'll attach the link to one of my videos for like an intro to the equilibrium constant. But essentially, you write out the concentration of the products raised to the first power because there's 1 mole of product, divided by the concentration of the reactant to first power because we have 1 mole of the reactant. So essentially, because we have a very high equilibrium constant value, that tells us that we're making a lot of products, right? Because the product is in the numerator. So if I want a big Kc value, I would have to have a very big numerator. So what that means is that this reaction is kind of heavily favored towards the products, right? If I just started out with maybe some reactants, well, this reaction would kind of go to the right, it would shift to the right, and it would create like a lot of products at this temperature. All right, and that's going to lead to a large Kc value. Okay, let's say that if I sort of flip this reaction around. So remember, the original reaction is A is at equilibrium with B. What if we have B is at equilibrium with A? How does that change the equilibrium constant, assuming that we have constant temperature? And the thing is that all you would have to do is you would just have to flip the equilibrium constant value. So in this case, right, the equilibrium constant for this reaction right over here is the concentration of B over the concentration of A, right? And you get whatever this value is. However, the equilibrium constant when I flipped this reaction is going to be the concentration of A over the concentration of B, right? You just kind of flip everything around. So that means that you also have to flip the equilibrium constant around in order to kind of make everything equal. You can think about this equilibrium constant as 9.8 times 10 to 11th divided by 1, right? And that matches up with what's here. However, if you flip this thing right over here, it's like you're taking the reciprocal of this, right? So then you have to flip this as well for the equilibrium constant. And yeah, that is what you get. Now, let's say that if we have a reaction, let's expand on this. Let's say if we have a reaction where 2 moles of A is at equilibrium with 2 moles of B, okay? And using this previous equilibrium constant value, try to find out the value for the equilibrium constant for this equation right over here at 300 degrees Kelvin. And yeah, once again, notice how I'm keeping the temperature constant because temperature changes the equilibrium constant. So I want to do these calculations without the effect of temperature changing. And I also want to make sure that in my equilibrium constant thing, I only have gases. I don't include solids or liquids there, only gases and AQ, okay? Anyways, if I were to write out the equilibrium constant for this, I would get this is equal to the concentration of B raised to the second power divided by the concentration of A raised to the second power, right? Because now this time they have 2 moles. There's 2 moles of each. I can rewrite this as concentration of B over the concentration of A raised to the second power in parentheses. We do know what the concentration of B over the concentration of A is equal to. That's equal to 9.8 times 10 to 11th power. So I could just substitute that in there. 9.8 times 10 to 11 to the second power, right? Because we have the square on the outside. So whenever you multiply a reaction by a certain unit, let's say from this reaction to this reaction, we multiply this by x units, well then the equilibrium constant would just be whatever your original thing was raised to the x power. Let's just say we have a reaction where it's at 400 degrees Kelvin this time. Let's say 1A is at equilibrium with 1B, 1B is at equilibrium with 1C. And these are the respective equilibrium constants. Now, if I add these two reactions together, right, notice how I'm going to get 1A plus 1B is at equilibrium with 1B plus 1C, right, if I add all of this together. However, the thing is that the B's aren't reacting in this case, right? So I can kind of just cancel them out, right, because in the context of this larger reaction, they are not really participating, right? I mean, they are, but it's like mainly the net reaction is just going to be 1A is at equilibrium with 1C. All right, that's just going to be the net reaction. The B's just like cancel each other out, right? Because there's one of it on each side. So the equilibrium constant for this reaction is going to be the concentration of C over the concentration of A. Now, originally, our equilibrium constant was the concentration of B over the concentration of A, right? That was the equilibrium constant for this reaction. And then for the second reaction, it's the concentration of C over the concentration of B, right, for this reaction. Notice how if I want to get from these two reactions to the third equilibrium constant expression, right? If I want to get from these two equilibrium constant to this final equilibrium constant, what I have to do is I just have to multiply these two together, right? Because the concentration of B divided by the concentration of A multiplied by the concentration of C over the concentration of B. If I multiply these equilibrium constants together, concentration of B cancels out. I just get the concentration of C over the concentration of A, and that's the equilibrium constant for this final value. All right, so when you're adding up the reactions together and you want to compare the equilibrium constant with what the equilibrium constant down here, all you essentially do is you just multiply these two equilibrium constants together. So in this case, the Kc value would just be 12 because 3 times 4 is 12. All right, so quick little review. If you flip the reaction, just take a reciprocal of the equilibrium constant. If you multiply it by some value, remember that you have to square it by that value. So because we multiplied our original equation by a factor of 2, now in this time we raise it to the power of 2, the original one to the power of 2. And finally, if you add up the equilibrium constants, if you add up these reactions together, you have to multiply the equilibrium constants.